Hello everyone, my name is Ayman El-Refai and today I'll present you our project, Sonar-Wave, a pervasive sonar-based hand gesture classification using CNN on smartphone, with my colleagues Ahmed Ibrahim, Mariam Abul-Ela, Sara Ahmed, and Mohamed Ibrahim. Our project is supervised by Dr. Hesham Eraqi and Dr. Mohamed Moustafa. Here's our schedule. The first section will talk about the problem statement and motivation for our project. In the second section, we'll discuss our system overview and architecture. Then from the third to the fifth section, we'll talk about the data acquired, its augmentation, and the dataset. Then in the sixth section, we'll talk about the deep learning models, which is the CNN and the results. And in the seventh section, we will show you a demo for our proof of concept. And lastly, we'll cover some of the challenges, limitations, the important outcome, and the conclusion. First, our problem statement and motivation. Our problem is that scientists are always interested in revolutionizing the human-machine interaction, also known as HMI. These advanced technologies are often expensive and require the latest technology, often making them inaccessible to the public. Thus, our proposed solution is to have an acoustic active sensing system to classify the various hand gestures a user can perform to work on a smartphone using the built-in stereo speakers and microphones without any extra hardware. Here are some of the existing solutions and research that tackle the same problem. The first is AudioGuest. AudioGuest uses the Doppler effect to classify hand gestures without any deep learning models or training. And the second is UltraGesture. They use the channel impulse response rather than the Doppler effect for classifying the gestures. However, they used extra hardware that uses up to 4 microphones other than the smartphone to achieve a high-grade accuracy. The third is Finger I/O. They used OFDM to track the finger movement rather than the hand gesture classification. And lastly, hand gesture classification paper, they use the Doppler effect and the CNN model. However, they use 2 smartphones to classify the gestures. So what makes our system different? First, it's a pervasive system that doesn't need any hardware modifications. Therefore, its implementation is much easier on current smartphone devices. Second, we utilize the stereo channels which allow feature fusion in the deep learning model, allowing many possibilities for more gestures. Third, we produced a rich dataset that contains more than 5 subjects and 2,000 samples available to the public that can be used for future research. Now I'll explain why did we choose the ultrasonic signal for gesture classification. Ultrasonic signal has received a lot of attention recently in many applications due to the following reasons. First, it has been thoroughly studied and has been applied on many applications, as it has a good ranging accuracy and a low-cost deployment. Second, ultrasound is non-audible to the human's hearing. Therefore, it can be in use without interfering with a person's normal life. Third, such sound signals are not affected by lighting conditions. Therefore, the system can work during the day or night without interruption, unlike other sensors, for example, like cameras. Therefore, we decided to use the ultrasonic wave to detect the hand gestures. Now that we have talked about the benefits of ultrasonic signal, let's discuss how our project is useful. One of the use cases for our application is enriching the VR experience in many ways. One of the problems VR smartphone users face is not being able to control the VR unless they have a VR controller. Our solution will allow people to use their hand gestures, allowing an immersive experience to navigate through existing options, such as scrolling, controlling the volume, playing or pausing a video. While such a solution may not be as effective as a VR joystick, however, it provides a cost-efficient alternative for users to interact with certain aspects of the VR environment without any extra hardware. Another issue is the inability for people with prosthetic hands or arms to control their smartphones. Although some bionic hands or arms could work with touchscreens, most of the time they are expensive or not widely available yet. Lastly, our system can be used in runner games that use simple movement, which can provide a new experience when gaming on smartphones. It can open the door for game developers to integrate such features to be a core part of the game.
Now we will be discussing the sonar architecture. We will now be discussing the specifications of the signal generated. We implemented the sonar wave using a continuous wave and a signal frequency of 20 kHz using the 2 speakers and the 2 microphones found on the Samsung 10E mobile phone. Shown here are the 2 different types of signals we've considered along with the continuous wave. The main differences between the 2 shown here is that the OFDM uses frequencies emitted multiple times during a specific time frame, which makes it harder to process and causes the signal complexity to be quite high. The chirp, on the other hand, uses a single frequency emitted over a time frame. However, there's not enough literature supporting its use, so we weren't able to accurately determine its pros and cons. The continuous wave, much like the chirp, uses a single frequency emitted over a period of time. This makes it great as it doesn't consume a lot of power and makes signal generation and processing quite easy for us. We found that compared to OFDM, the signal here is often consistent with little to no signal loss. The downsides are that it is much more vulnerable to background noises than OFDM and doesn't work well with long distances.
After the signal is generated, a hand gesture is performed in front of the smartphone. Once the signal received from the microphone, we are mainly going to be looking for shifts in the frequency time domain to understand the changes. So we mainly measure the frequency shift by the Doppler effect. According to the Doppler effect, different frequencies are generated from different motions. For example, the frequency will be high if the hand moves towards the smartphone. These frequencies will be modeled to the spectrogram as example shown in the slide, so we can recognize the type of hand gestures. Here is our previously shown smartphone sonar architecture. We use smartphone speakers to generate the sound signal, which is composed of sample rate of 44 kHz and frequency of 20 kHz. To adjust the sample rate and the frequency, the sample rate is double the generated frequency to achieve oversampling, which improves the signal-noise ratio and avoid aliasing effect. After that, the noise wave is produced as PCM pulse code modulation file, which is output by the speaker of the smartphone. This sound wave is reflected by the hand gesture and is inputted to the smartphone. The application inputs the recorded audio stream into a byte buffer. Then we had to convert the recorded byte buffer into a .wav file format used for audio. Then we applied the STFT to display the waveform. Now the data collection. Before going to the procedure of data collection, first we would like to show you the supported gestures in our project. We have 6 gestures, which are swipe right, swipe left, swipe up, swipe down, push inward, and lock the microphone. For the data collection, we collected 1920 gestures, which were produced by 4 different subjects. Each one collected 80 gestures for each type of the 6 gestures. And for the test data, it has been collected by 3 subjects and 30 gestures is collected for each gesture type. Moving to the data augmentation, we doubled the training data to be 3840 by the following methods. First type of data augmentation is Gaussian noise. Gaussian noise is statistical noise with a function of equal probability density in the Gaussian distribution. Based on the literature, Gaussian distribution is highly preferred in machine learning because Gaussian random events are very common in nature. While observing random events, which is the sum of many independent events, all random variables appear to be Gauss variables. That's why we choose to apply Gaussian noise. To add the Gaussian noise, we need variance of random distribution, which is equal to the double of the standard deviation. So we tried different values of variance in order to obtain clear image with Gaussian noise. It found that the smaller the variance, the clearer the image with Gaussian noise, as shown in the figures in the slide. Hence, we chose the value of 0.01 in order not to damage the data of the spectrogram. Second type is sharpening. Image sharpening is an enhancement that highlights the edges of the image. We need this technique because the energy is centered in the low frequency parts of the image, and the noise mainly in the high frequency band. Also, the edge information is centered in the high frequency part of the image. As a result, the image will be blurred. Therefore, we use sharpening technique to clear the edges of the image, as shown in the figure in the bottom of the slide. The lower the factor of enhancing the image, the blurrer the image. So we give the enhancer factor of 20 to increase the color of the image to highlight the edges.
Lastly is the noise injection. We've taken the feedback from our last progress presentation and decided to inject noise into our wave files. We found that overlapping 2 sounds was unhelpful as the other sound would often be quite low. So we decided to inject a random range of numbers into the time series data of the wave files. As shown here, in the image we've tested multiple variables and found that using a standard deviation of 0.0015 created a realistic amount of noise for our model. That standard deviation can be found in the middle image.
And now we'll talk about our dataset. Regarding our dataset, it consists of 6 types of gestures. It also consists of around 2,600 files of audios and images of spectrograms, where 2,000 were used for the training data and 600 for the testing data. Also, the data includes both stereo recording and the 2 mono recordings for the respective microphone. Now we will talk about the deep learning models and the results we achieved. Regarding the inputs to the model, we introduced 2 different types of inputs. The first is the stereo spectrogram, where we get the dot wave stereo recording and convert it into a spectrogram as shown on the right. The second is either the top or the bottom spectrogram, which is achieved after splitting the stereo dot wave file into 2 files, and then each converted into its respective spectrogram. As an example, we show here a gesture, which is blocking the bottom microphone. As you can see on the right, the stereo spectrogram shows an effect on the 2 microphones. However, if we look further on both microphones separately, we can see that the bottom microphone is much more affected compared to the top. Such inputs will be an integral part in our decisions for the deep learning models. Also, all the tests done to our models are based on the test data, which included 3 new subjects that weren't a part of the training data. We here show our first attempt to create our own CNN model architecture based on the literature. We input a grayscale version of the stereo spectrogram since research showed that RGB channels would increase the computational power and will not provide any useful features to our classification. The model, as shown, consists of 5 convolution layers, each followed by a max pooling layer. Then at the end, we flatten the output and we connect it to a fully connected layer. We use the softmax as our activation function. As mentioned, the architecture is influenced by the literature, and we tuned the hyperparameters to obtain the best accuracy. Our accuracy achieved with this model was 81.7%. After trying with our own CNN architecture, we then experimented with transfer learning by using different pre-trained deep learning models, and we achieved the best accuracy with exception CNN model, which will be our main model going forward. The exception model was created by Google. We fine-tuned the exception model to work with our dataset. We also used it with the pre-trained ImageNet dataset since it produced better results than the untrained exception model. Our first attempt was to input the spectrogram as an RGB image, due to the nature of the pre-trained model requiring an RGB format. Also, in another attempt, we also inputted the spectrogram image as a grayscale. However, as 3 channels were required considering the model takes an RGB format, we concatenated the same channel 3 times to have a grayscale be a 3-channel image to work with the pre-trained model, while keeping the grayscale color range. The results showed that concatenating the grayscale spectrogram image produced better results than the RGB spectrogram image, and thus we opted with the grayscale image in all our models. Our highest accuracy achieved here is 87.15%. Now for our third model, we introduce early fusion using exception model. The structure of this model is similar to the previous exception model. However, the difference here is in the input. Instead of using the stereo spectrogram as a 3-channel, the input in this model comes from 2 sources, the bottom and top spectrograms and the stereo spectrogram as well. As the exception model requires a 3-channel input, we concatenated the top microphone spectrogram, the bottom microphone spectrogram, and the stereo spectrogram. Therefore, forming a 3-channel image we can input to the model. We achieved here an accuracy of 93.58%. These are the confusion metrics of the basic exception model and the early fusion model. The highlight here is the accuracy of the up-down gesture. The issue of using a stereo spectrogram was that we had no clear difference of which microphone was affected more. For example, on the left we can observe that the up-down gesture is mostly confused with the right-left gesture. However, on the right in the early fusion, we have separated the spectrogram for the top and the bottom microphone, and thus we can distinguish which microphone was heavily affected and identify the gestures accordingly. As the right-left gesture doesn't pass by the top microphone and mostly affects the bottom microphone, while the up-down gesture affects the top microphone and the bottom microphone as well. And here we can find a clear distinction. Here we show the last attempt in our deep learning models. This was another attempt to utilize the top and the bottom microphone through using late fusion CNN model. For consistency, we use 2 exception models, where we take the separated spectrograms of the top and the bottom microphone and train each separately, and we then concatenate the output of the 2 models to get the result. We achieve here an accuracy of 92.19%.
Now the demo section. After showing you all the system components and the results of our models, there is one final thing before going into our demo. We'd like to show you its setup. Our setup is a client-server architecture where the smartphone is the client. It records the gesture from the user and sends it as an audio file for processing on the PC server. Then the PC processes the audio file and extracts the gesture using the deep learning model. Lastly, we set up listeners that monitor any file changes on both devices, so once the audio file is ready, it's automatically sent to the PC and processed immediately. You have seen earlier a demonstration of the swipe left gesture. Before going into the rest of the gestures, let me show you how the setup works. First, we must start the PC server listener to monitor the file changes, so it's ready when the smartphone sends the audio file. Next, we have to run a bash script on the smartphone to monitor the file changes, so once the gesture is recorded, it's immediately sent to the PC server. Lastly, we have to start our ultrasonic generator, which is the smartphone. Now the system is ready to capture the gestures, and we will demonstrate the rest of the gestures in a noise-free environment. Now the user is performing the gestures. The screen is displayed on the bottom left where it shows the updates of the gestures performed by the user, and the system is capturing all gestures perfectly without errors. Here we will demonstrate the rest of the gestures in a noisy environment to test the system's robustness under noise. On the left, we play a sound effect of people talking on maximum volume, and then we normally perform the 6 gestures. You will see that some gestures, such as the swipe up and down, don't work correctly from a distance, and this happens because the smartphone's microphones are not strong enough to capture the change in the Doppler effect. Nevertheless, in most of our applications, the user is nearer to the smartphone.
We will now be discussing the challenges and limitations. We found our model to have 3 main challenges. The first is that the interactions must be near the microphone. The second is that we have implemented it only on limited gestures and interactions, 6 as described above. And achieving real-time performance is also a great challenge. Our limitations are that any disruptions to the speaker will cause disruptions to the emitted sound, and noisy environments with high-pitched sounds can affect the accuracy. For example, when sitting in a coffee shop, coffee machines have high-pitched noises that could affect the accuracy of our model. The third is that you must turn off other sounds from the smartphone or use headphones as not to disturb the sonar wave.
And now we will talk about environment outcome and contributions. We have satisfied our main outcome, which is doing a research paper. We also created a rich dataset that involves over 2K audio files and spectrograms. We used single smartphone compared to the previous research that either used one smartphone with extra sensors or hardware, or two smartphones. One acts as a mic and the other acts as speaker emitting the ultrasonic sound. We also utilized the top and bottom microphone by using feature fusion, which gave us much accurate results. Regarding the conclusion of our research and future work, we concluded that separating the audio files into two separate channels has resulted in much better accuracy for the classification. Regarding our future work, utilizing both mics will give us a space and more room to include more gestures. We also think of increasing the dataset size that has more additional subject to make the dataset more diverse and rich. And finally, add more different smartphone models, as we only worked on only one model. And these were our references for the research. Thank you for your attention, and please feel free